Our presenter today is Mike Lewis. Mike graduated with a mechanical engineering degree from the University of Illinois and received his Illinois Professional Engineering license in 1984. Mike's early career was in consulting, design, and construction, where he was actually a customer of Fisher and Novaspect. Mike brought his talents to Novaspect 29 years ago and is now sales management and severe service specialist. But throughout his career, he's had a passion for helping customers with their critical valve needs and engineering the right valve solution for the most difficult applications. His passion and expertise is well renowned across the Fisher valve community, where he's often asked to present on severe service valves to groups from around the world. We're very fortunate to have Mike with us today. So, welcome, Mike. Thanks for being here and sharing your thoughts with us. I'm going to turn it over to you now.
Thanks, Robert, and thanks to all of you out there for joining us this morning. I personally selected the subtitle for this presentation, Keeping Your Control Valves Off the Monday Morning Meeting Agenda, and that's because I have been involved in some customers' Monday morning agendas, some because I'm more or less an unpaid staff member, others because I brought donuts, and unfortunately for some of them, we had some of my valves to discuss. So I'm familiar with Monday morning meetings and enjoy being in them. Invite me to yours, okay? All right, our topics of discussion today include the definition of a control valve, a plain old everyday control valve, and the design parameters that are used to determine which valve is required for use, and then get a little more specific regarding severe service applications for control valves, which include erosion, corrosion, cavitation, flashing noise. We'll discuss some engineering, installation, and maintenance considerations for those types of valves, and then we'll have time for some questions. If the big blue area on your screen were to represent the universe of all the control valves in your plant, we might find a couple subsets of this universe. One we would call control valves that are critical to profit. These are the valves that, based on how well they work, either make you production dollars or lose you production dollars. And they do that essentially by controlling the variability in the measured variable that you're trying to control. They either control them flat dead on line, or you get a lot of variability, and if you get variability, then you get poor throughput, poor quality, etc. The other group of valves are the severe service control valves. These are the ones that experience the phenomena that I told you about earlier. These valves generally have a very high acquisition cost, and they have very high costs of maintaining them over time. The intersection of these two sets of valves is the stuff that Monday morning meetings are made of. And indeed, these are the valves that require our best work as a team, you as the needer of a control valve and us as the supplier of the control valve. A basic definition to get us all grounded in terminology: a control valve is a power-operated device which modifies the fluid flow rate in a process control system. It consists of a valve connected to an actuation mechanism that is capable of changing the position of a flow controlling element in the valve in response to a signal from the controlling system. You see the components there of the control valve. We'll talk more about these in detail, but what's important to know is that the control valve itself does not control pressure. It does not control temperature, conductivity, pH. It controls flow, and as a result of controlling flow, it controls the measured variable that you need to have on set point. Almost every control valve is part of a feedback control system in which we measure a variable, like, for example, this could be the steam pressure, P2, in a downstream of a control valve. Our objective is to control that pressure. We could have something as simple as a pneumatically operated pressure controller. For example, you might be familiar with the Wizard pressure controller. There's a knob in there which you use to set the set point for the pressure you'd like to see in pipe P2, it sends a loading pressure to the actuator, which positions the valve plug against the seat ring to a certain position so that just enough steam gets through this P1 to P2 to maintain P2 at the steam pressure where you want it, regardless of what the load might be. If you go down there and you grab that valve called the load valve, you change its position, this whole system, this feedback control system will respond to restore the pressure to the set point. Could be a little bit more elaborate, this system. It's still a 3-element control system, but we've got some electronic components instead. You probably would have a Rosemount 1151 differential or pressure transmitter attached to the steam pipe measuring pressure P2. It would send a 4 to 20 milliamp control signal to the, hopefully it's a Emerson Delta V control system, and that system would be sending out that red dotted line, an electronic 4 to 20 milliamp signal to the valve assembly to position the valve appropriately to get the right pressure. And of course, your operator is sitting at a console, and via push buttons, he or she is selecting the pressure that we want this steam header to be at. A little further deeper into the control valve assembly itself, the actuator is the device that receives a pneumatic signal of varying analog value, typically 3 to 15, 6 to 30 PSIG, 0 to 45 PSIG, whatever we've engineered the actuator to do. And the sole purpose of the actuator is to move the plug in the control valve up and down relative to a seat ring in order to allow a particular flow through the valve. The actuator usually has a fail mechanism, fail open or close, but it does not always have to have that. The valve body, of course, has the most important components of the valve, which are what we call the trim components. And these are the movable and stationary pieces inside the valve that essentially determine the valve characteristic for flow. Many control valves, not all, but most control valves also have another device called a positioner. These could be electronic, could be pneumatic, they could be field bus. But the positioner's responsibility is to receive the input from the controlling system that tells it how far the valve should be open, and it actually gets valve stem feedback, so it knows what position the valve is actually in, and it continues to run a little control system within that adjusts the air pressure to the actuator so that the plug ends up in the position that's commanded by the control system. And of course, that signal is designed to achieve the pressure downstream that we wanted, P2, in the last slide. If you were to look at the internal valve trim components in the valve, there are various different forms. We call them balanced trims, unbalanced trims. They're guided with cages. They're guided with bushings. A lot of different styles depending on the application. But what you need to realize is that it's nothing more than a variable orifice. The blue element, the plug, moves up and down as commanded by the actuator, as commanded by the positioner, as commanded by your control system. And we move the plug more or less against the seat ring, and it's just a variable orifice. I'm showing you globe valve trims on this slide. All control valves are not globe valves. Butterfly valves, V-balls, eccentric plug valves, these are all various types of control valves that you would find in your plant. But we'll talk mostly in terms of a globe valve. Let's talk about the basic control valve selection parameters for any valve. This would be any valve that's in your universe of control valves in your plant. We need to employ certain engineering practices to make sure that we pick the right valve. First of all, of course, we're concerned with the size and the turn-down capability of your valve. So we go through a process which we call the sizing process. Maybe many of you out there even have Fisher or other software on your computers, and you try to accomplish this task on your own. In essence, we're inputting a bunch of process data and thermodynamic characteristics about the fluid that flows through the valve, and we're calculating a sizing coefficient, and from there we look at our charts and pick a valve size that's appropriate to the application. And hopefully the same valve works well at the max flow condition and the min flow condition. Another very important aspect of design of a control valve is the ANSI class. It has influence on the pressure containing parts. You have a design pressure and a design temperature for any piping system. The valve, being a part of the piping system, of course, has to obey the same design requirements as the pipeline that it's installed in. So you can usually go to your piping design documentation and find what the ANSI class is for any valve in the system. The difference between two control valves that are designed for two different ANSI classes essentially is a matter of wall thickness. You can see the picture on the left is the ANSI class 600 valve. That valve has very thin walls compared to an ANSI 1,500 pound class valve. Obviously, the valve on the right, the 1,500 pound class valve, is designed to handle much higher coincidental pressures and temperatures from the design basis. We need to know the process fluid temperature. In addition to the wall thickness issue, we've got a bunch of parts inside that are not even actually pressure boundary parts, and therefore they're not part of the ANSI pressure class consideration, but nevertheless different metallurgies of parts in the valve have different temperature characteristics as far as how much temperature they can stand without degradation. And not every part in the valve has exactly the same temperature characteristics, so any valve that we pick, we have to look at what is the temperature capability of the part in there that has the lowest temperature and make sure that at least that one is above the design temperature for the valve. In addition, some valves open and close frequently and they heat up and cool down quickly, and therefore we get thermal gradients in the valve over time. And some parts, depending on their materials, have different thermal coefficients of expansions than other parts that might be in the valve. And therefore, as the valve heats up and cools down, we have to pay attention to the rate at which each part shrinks and expands so that we don't end up with parts that stick together and make it a poor control valve. Another very important attribute that needs to be considered for a control valve is the pressure drop across it. We're going to spend a lot more time talking about the pressure drop because the pressure drop across the valve is the parameter that most obviously determines how severe is the service for a valve. But even in the everyday general service valve, we need to consider the effect of the pressure drop across the valve on the internal components of the valve. As you would expect, pressure difference across a component times the area of the component is a force. Pressure times area equals force. So differential pressure across areas in the valve will produce various forces that are detrimental: bending, shearing, things of this nature. It could be a globe valve. We want to twist the plug off the stem. In a butterfly valve, we might actually want to break the shaft and let the butterfly valve disc go downstream. Another important characteristic that you need to identify for us is the ANSI shutoff classification. We like to think of your control valves as just that, control valves. And indeed, the control valves' basic design criteria is to be a good flow controlling element and to do that with the minimum amount of variability. But sometimes you want to save some money and you want to assign a particular shutoff classification to the control valve simultaneously. So there is an ANSI specification that you can reference, and we certainly know all about. In there are defined various levels of leakage classes, essentially 2 through 6. And each one of these has a particular way of testing the leakage and a particular acceptance criteria. And you can assign to your valve manufacturer the need to have a particular control valve not only control well, but also shut off to ANSI Class 4 shutoff, for example. One point I want to make about this, and we won't dwell on this a lot as a severe service consideration, but don't over-specify the shutoff requirement for your valve. If you specify a Class 5 or 6 valve when actually a Class 2 would suffice, we do a lot of design differences to that valve. Everything gets bigger, the bonnet gets bigger, the stem gets bigger, the actuator gets bigger to provide bigger thrust to push plugs against seats with more resilience. So everything gets bigger and more costly if you specify a very tight shutoff valve. So if it's good enough that it's a control valve and it doesn't really need to shut off, call it an ANSI Class 2 valve, and only pick tight shutoff when you absolutely need it. We prefer that you use a motor-operated gate valve or manually operated gate valve or something like that if you really need tight shutoff during long periods of time. Your piping design specifications will also indicate for you, for any pipeline that you're going to put one of our valves, that the valve needs to have particular end connection style. These could be screwed or socket welded or flanged or butt welded. Even the flanges are various types, raised-faced, ring-type joints. So go to your piping design specifications and find out what end connection is required for the valves in that pipeline, and that's a piece of data you want to give your valve manufacturer when you need a new valve. Believe it or not, your valve manufacturers do know that price does matter, and various control valve architectures cost considerably different amounts of money. As you can see, a butterfly valve is a fairly low-cost device. A globe valve, in comparison, is a pretty high-cost device, and a ball valve, kind of segmented ball valve, fits in between. We want to use the right valve that provides the level of process control accuracy that you need to stay on set point and keep you profitable. And we don't want to spend any more of your money than we need to in order to accomplish that task. And we certainly don't want to cheapen up on the valve that we use in a process that's critical. So we might sometimes, valve manufacturers suggest, yes, you can save money with a butterfly valve, but this application requires something more appropriate to good flow control. So listen to your valve manufacturer in these issues. Your maintenance staff might have some particular preferences regarding valve types that you might use. From a maintenance standpoint, a top-guided, top-entry globe valve, here that I'm pointing to now, is very easy to maintain while the valve is in line. You merely unbolt the bonnet from the top of the valve and pull it off, and you get access to every one of the components in the valve, all the gaskets, plugs, cages, bushings, seat rings, stems. It's all available there for you to inspect and repair as required. Unfortunately, rotary valves don't have that same benefit. Anytime you need to inspect or repair or replace a part in a rotary valve, it has to be removed from the line to get access to the internal parts. So, you know, your maintenance staff may have something to say about the type of valve you use in any particular application. But the basics that I just discussed that are just for any valve, control valve in your plant, are just the beginning of the things we need to worry about for a severe service valve. Yes, we need to worry about all of those things, but in addition, we've got concerns about erosion and corrosion damage. I have some pictures of some parts here that have been damaged by erosion and corrosion. They generally look really nasty. They can fall apart quite quickly. We need to find ways to combat this. For erosion, we can try to erosion-proof your control valves by the appropriate selection of very hard materials for the trim components. Maybe even the body itself needs to be made of a very hard material. Maybe we have to have a hard liner inside to resist the effects of these particulates that are coming through that are wanting to erode the valve away. Sometimes we'll use a particular valve architecture. We might use an angle valve instead of a straight-through valve in order to make the fluid not make so many turns within the valve, so that we don't give an opportunity to these erosive solids to spend much time in the vicinity of metallic parts, basically get the flow straight through the valve. We might use a straight-through valve like a butterfly valve or a segmented ball valve, because it's a line-of-sight valve. If I picked it up and looked through it, I could see right through it, compared to a globe valve, which has a lot of twists and turns. And we control the clearances of valves that are going to be used in erosive services. Gritty substances will have a tendency to want to collect in places that have close tolerances, thus kind of restricting the motion of the moving parts, and that will make a bad control valve. So these are some of the ways that we erosion-proof one of your control valves in that kind of a service. Corrosion proofing is a little different. It requires that you do as complete of a fluid analysis as you can regarding what's flowing through our valve. You're in control of that. Only you know what those constituents are, and it's important that you discuss with your valve supplier what those are. Is in the way of a corrosion analysis, you would probably do some kind of a time, temperature, concentration, and agitation analysis to know the effect of that particular fluid on the metals that we might use for construction of a control valve, or your piping system for that matter. you probably determine what's an acceptable operating life. In other words, you might figure out how many mils per year of metal loss are acceptable, how long you're willing to wait before you throw away the control valve or the piping system that you've installed. You have to calculate the total cost of ownership of that equipment based on it corroding away. You have to consider that there are consequences of a leak to the environment. You know, if you got a toxic or corrosive fluid being held within the valve in the piping system, you want to know what are the consequences of a leak to the environment from an environmental standpoint, a safety standpoint, health standpoint. More often than not, your particular industry or your company has a lot of experience-derived metallurgical solution ideas for what you would build a piping system or a valve out of. And to be truthful, all valve manufacturers' last resort, and the way we like to do this, is to ask you, what is your company's or your industry's experience with different metals for different fluids? And at the end, all valve manufacturers defer to your advice regarding what the right metallurgy would be in your valves. Well, erosion and corrosion are pretty nasty, and they make quick work of control valves. Let's discuss a couple other flow anomalies that really create problems for us and have us replace valves more often than you, the customer, would think we need to, and more often than we would like to ourselves. So we have flashing and cavitation phenomena, and the cause is similar for both, but there's a little difference in the process that creates flashing and cavitation. The picture on the right is indicative of flashing damage. If that plug were made out of clay and you took a popsicle stick and started carving, gouging long pieces of that away, you would end up with a plug that probably would look like flashing damage. Usually it's a very shiny look and crevasse in nature. Cavitation damage, on the other hand, looks completely different. It's characterized by kind of a pitted lava rock, pumice stone look to it. It's quite obvious when you see it. And you would probably find, if you pulled the plug out of a valve and saw it look like the one on the left, you probably noted while the valve was in operation that it sounded like gravel running through the pipe. And that is the sound of cavitation, and we're going to talk about what exactly is cavitation here in a couple minutes. In addition to all those four things we've discussed, somebody worries about noise. It's usually you. It's most often the valve manufacturer, but you've got OSHA laws, corporate practice, good neighbor policies. All of these things determine to what extent you need to attenuate the noise that's produced in a control valve or anywhere in your process for that matter. Valve damage is something that occurs if noise levels are too high. Essentially, we convert valve noise to mechanical vibration, which results in parts banging around, and they wear out quite quickly. So even if your particular process doesn't seem to be too severely affected by any of those top three issues, OSHA, corporate practice, or good neighbor policies, I can guarantee you that your valve manufacturer is going to tell you when you're exceeding what we think is a safe noise limit for the health of the valve. We learn about some of these severe service issues during the process of sizing the control valve. So let's talk a little bit about the sizing process. During the sizing process, we make sure that the valve, of course, has sufficient capacity to pass the flow that you've defined for us through it. We like it to be within the normal realm of the throttling capability of the valve, maybe 20 to 80%, let's say, so we get accurate control and we get stability in the process, measured process variable. We want to minimize wear and minimize costs. So how do we size? Well, the sizing theory is that we mathematically convert the flow rate of a process fluid to an equivalent flow rate of a reference fluid, which happens to be water. And then select a valve size known by test to be capable of passing the reference equivalent at the process conditions specified. this is it. We take your process conditions, a little bit of fluid dynamics theory, which essentially is derived from some physics. We take some experimental data regarding the valve type itself, the specific valve, and we do this in the factory. We run our valves through some very exhausting flow tests in our flow laboratory to determine various critical constants regarding it. We put that all into an algebra hopper, and we end up predicting the right size. And the size of the control valve is measured by the CV value that it needs to pass. By definition, 1 CV is equal to 1 gallon per minute of 60-degree water passing through the valve, which has a 1 psi difference in pressure from the inlet side to the outlet side. And I'm sorry to do this to you, but we couldn't possibly get into a discussion of flashing and cavitation unless we review a basic law that applies to these processes. The first law of thermodynamics very succinctly is related to Q, the heat transfer into or out of a process is equal to the change in internal energy, which is essentially the molecular activity due to the temperature. Something that's at high temperature, the molecules are bouncing around a lot. If it's cold, they kind of lay there dormant. Well, that's the internal energy. The kinetic energy, the change in kinetic energy, is essentially related to the change in velocity. If I have a fluid stream flowing at 10 feet per second, yeah, I can shoot my hose against a piece of metal and blow that piece of metal 10 feet away. If I've got a fire hose, I certainly have a lot more energy there. So that's what kinetic energy is. The PV energy, that's the pressure volume energy. That's the work at our pump, for example, that's required to raise that certain volume of water from a low pressure to a high pressure. The Z, delta Z, is the change in potential energy due to elevation. A bucket of water that's sitting on top of a building has a lot more potential than a bucket of water that's sitting on the ground. Imagine that I were to poke a hole. It's in a column of water that's as high as a building. It has a lot of pressure in the bottom of the bucket, and I'll have a great fluid stream, and I'll be able to turn a turbine a lot faster than if the bucket of water is no higher than the ground. So delta Z does matter. And W is the work that's available from the system. This equation can run either way. We can either get heat out by putting work in, or we can put heat in and get work out. So the positives and negatives, of course, apply all through this equation. But what's important is we can take the first law of thermodynamics and we can get rid of everything from it that's not applicable to fluid flow along a streamline, which is really what we're talking about today. It's a streamline of water or propane or ethylene glycol flowing through the control valve, a streamline. And most of the terms in the first law of thermodynamics disappear except for the PV, the pressure volume energy, and the change in kinetic energy. These are the two terms that are left in our equation, and the law would be that the change in PV energy plus the change in the kinetic energy have to equal 0. One has to offset the other. We can rewrite this equation for fluid flow along a streamline. The PV energy is essentially pressure in PSI, for example, divided by the density, which would be pounds per cubic inch. The velocity, of course, is feet per second or feet per inch or whatever you want to call it, and G is the gravitational constant, 32.2 feet per second squared. If you were to run all the math on the units there, you would find that the answer, each of these components is measured in terms of feet of head. But the equation says that the sum of the pressure head, P over rho, plus the velocity head, 1/2 V squared over 2G, cannot change. It has to equal a constant. If I were there with you now, I'd have a whole bag full of $100,000 candy bars, and I'd be throwing one of them to whoever could properly answer this question. The test question is, what is this law known as? And I'm going to give you 1 second. Time's up. I bet the U of I graduates out there know that this is the Bernoulli theorem. And I'll go back to that. It relates conservation of energy along a streamline. It says that the pressure head goes up, the velocity head has to go down because the sum of those two have to equal a constant. All right, let's talk about liquid sizing theory a little further. The equation for sizing a valve is in this green box. The Q in gallons per minute equals the CV times the square root of the differential pressure across the valve divided by the specific gravity of the fluid. The differential pressure, again, is the difference in pressure between the pressure at the inlet of the valve and the pressure at the outlet of the valve. If we were to plot that equation with Q on the y-axis and square root of delta P on the x-axis, we'd end up with a straight line with a slope equal to CV. Okay? That would suggest that if we can raise the differential pressure across the valve to infinity and beyond, as Buzz Lightyear would say, that would also raise the flow rate of water through the valve to infinity and beyond. That, in theory, is a great idea, but unfortunately, in reality, that's not what happens. What happens is that we reach some point as differential pressure increases more and more, we reach a point where theory falls apart. And what happens is we reach a condition called choke flow. And at choke flow, vaporization is occurring. Water, let's use that as an example, the fluid is flowing into the valve, and we drop below the vapor pressure of the fluid, and vaporization, we boil, to put it in simple terms. Boiling of the water to steam occurs within the valve, and you can see that there is a constant that we call F sub L. That is the valve geometry coefficient, or the valve recovery coefficient. Some people call it different names. That is the coefficient that determines for any given valve in any given application where is the point along the delta P x-axis where this departure from reality, from theory to reality takes place. And this is important to know this because it helps guide us in our selection of a control valve to address this problem. All right, we've talked about the differential pressure across the control valve. I should tell you that I've had personal experience, and therefore I have to take time out for this lecture. Forgive me if this is under your head, many of you. But I've had customers call me and say, "Hey, Mike, I need a valve. It's got to deliver 100 gallons per minute of water. I've got a 2-inch pipe, but it's got to deliver 100 gallons per minute of water over to my demineralizer and 60-degree water." And I say, "Oh, that's great. Can you tell me what's the valve inlet pressure and the valve outlet pressure while I'm delivering that 100 gallons per minute through the valve? I need that to do the sizing of the valve." And he says, "Well, Mike, that's your valve. You should know the differential pressure across the valve." And what we have here is a failure to communicate. We have a failure to recognize that we have too many unknowns and not enough equations to solve them. And actually, you are responsible for knowing the P1 and the P2, the valve inlet pressure and the valve outlet pressure, and you have to tell your valve manufacturer what that is as a function of flow if you want to end up with the best, most perfect control valve. So let me explain how this works. We've got a little graph there called the centrifugal pump performance curve. On the y-axis, we have TDH. That's a pump curve that would be called the total developed head, or total dynamic head, some people call it. It's measured in feet of liquid pumped. The x-axis is Q, the flow rate that the pump delivers. Every centrifugal pump has essentially a characteristic that provides for decreasing pressure that we can pump against with a need for increasing flow. The more flow we've got to get through the pump, the less pressure it can do that against, and that's where you see the droop in that green curve. We need to do a hydraulic balance, so we need to know how much pressure that is created by the pump is eaten up due to friction in the piping system. You can see I've labeled two pieces of pipe up there, L1 and L2. I need to know how much pressure do I lose in those pieces of pipe. The equation that's used to do that is called the Darcy equation. It is that the head loss equals F, a friction factor, times L over D, that's an equivalent length of pipe, times the velocity squared of the fluid in the piping system, again divided by 2G, G being the gravitational constant, 32.2 feet per second squared. H is measured in feet. It's really nice that H is in feet because it allows us to lay curves on the same graph as long as we're talking about the same units, which is feet in this case. This is a little more complicated because F, the friction factor, is a function of the Reynolds number and the relative roughness ratio of the pipe surface in the interior of the pipe. Well, this is more complicated because the Reynolds number is a function of rho, the density, V, the velocity in the pipe, D, the diameter of the pipe, and mu, the absolute viscosity of the pipe and centipoise. Maybe you're starting to sense here that we have a lot of interrelated parameters that are going to change as we change other things. Sizing a control valve is a very iterative process. You have to plug and chug, re-plug and chug, re-plug and chug. Thank God we have computers that do that now. One more complication, the L over D is essentially the equivalent length of pipe. So if I have a piece of pipe that's 100 feet long and its ID is 1 foot, I essentially have 100 L over Ds. A control valve has a certain number of L over Ds. A gate valve is rated in terms of a certain number of L over Ds. You might find, if you look in various texts that talk about this, the coefficient K. K is another way of expressing L over D. The K factor for any fitting or valve or whatever, an orifice, is nothing more than F times L divided by D. So maybe you're not familiar with L over D, you're familiar with K. The relative roughness ratio is a function of the diameter, the internal diameter of the pipe, and the material the pipe is made of. So we've got a different relative roughness number depending on whether the pipe is concrete or plain carbon steel. So, man, is there or is there not a whole bunch to think about when it's time to size a control valve and determine what the inlet pressure and the outlet pressure is? And I must say that all this stuff is your responsibility. I want you to notice something about Darcy's equation, the V squared term. In essence, we have an equation that, if you remember your, what do you call that, your analytical geometry, y equals mx plus b is the equation of a straight line. Well, this is not a straight line because it has a V squared term in it. This is a parabola, and you probably learned that in analytical geometry. So the friction loss in a piping system, H, the amount of pressure loss, is proportional to the square of the velocity. So let me just paraphrase that. Let's say you want to double the flow rate through an existing piping system. 2 squared is 4. That means you're going to get 4 times the friction loss in the piping system if you try to double the flow. What if you want to triple the flow rate in your piping system? Wow. You're going to multiply the existing friction loss that you used to have by 9 in order to get the new friction loss in the piping system. You can see when you try to increase flow, you quickly lose pressure in the system. Let's do our hydraulic balance, okay? We're trying to find out what our P1 and P2 are. I'm trying to help you understand how you do that so that you can tell your valve manufacturer what those numbers are. What is the suction pressure at the pump? In essence, let's say that's a short piece of pipe, this little green piece of pipe. It's almost infinitesimal. The suction pressure at the pump, therefore, is equivalent in feet to the head of liquid in the tank from which we get the suction. So that's the pressure at the suction of the pump, PS equals Z1. The discharge pressure of the pump is equal to the suction pressure at the pump plus the total developed head at any particular flow rate as determined by the performance pump curve. So it's PD equals PS plus TDH. You okay with that? I hope so. What's therefore P1, the inlet pressure for the valve? That's the number that I want to know. Well, P1 is obviously equal to the PD, the discharge pressure of the pump, minus the amount of friction loss that I have in the piping system, L1. What is P2? It's equal to the pressure in my end point, my reactor at the end of the line here, plus the elevation head Z2, plus the friction loss in the piping system called L2. Let's solve for the dP across the valve, P1 minus P2. Look at every one of those elements. They're elements that we just discussed. Not one of those elements has anything to do with the valve that I would pick. None of those coefficients are found in none of those are coefficients, and none of those are found in manufacturers' control valve catalogs. All of that is your information, and therefore, in order to predict P1 and P2, you need to do a hydraulic balance. And ideally, you do that balance at a minimum at 2 flow points. The max flow you expect this valve to handle and the minimum flow you expect this valve to handle. I was asked to increase the capacity of a reheat spray valve, and we did this analysis. I actually walked off all the pipe, counted all the elbows, the T's, every fitting, run T's, branch T's. Are they short radius elbows, long radius elbows? All of these have different K factors. When you sum up all the K factors, then you can do your head loss, your Darcy equation. And we actually predicted that even though he wanted 25% more capacity out of his reheat spray valve, he was burning Powder River Basin coal. All of the sooting that was going on was slagging the furnace walls. Heat transfer was moving from the furnace walls up to the reheater area. He had trouble keeping his temperature down, and he thought I could help it by providing more spray water. What we demonstrated to him was that we could essentially take the control valve out of the pipe and just put a short piece of 12-inch long piece of pipe in there, and he would only get 7% more flow with no valve. So he wanted 25%. We demonstrated by doing this hydraulic balance that there was no way he could achieve his objective. These are the kinds of engineering tasks that I hope you guys are doing in your offices when you need a new valve. The role of the control valve in the process is to create resistance and use up additional pressure drop. The blue line is the total resistance, the hydraulic balance, if you will, of a process without including the control valve, and that red curve is a centrifugal pump performance curve. The difference between this point and this point is the number that your engineer used when the plant was designed as far as how much pressure drop did we tell the valve vendor at that particular point that we were going to allow him to consider across the valve to get the flow rate through the valve. When we have to throttle the valve to a more close position in order to keep your process variable on set point, in essence, we're grabbing this blue curve here, which was the wide open control valve curve, and we were dragging it over until it's now in the position of the dotted line. You can see, where do we operate now flow-wise? We operate at the intersection of the new hydraulic balance curve and the pump performance curve at this point, and this is the flow rate we're delivering at that point. What is obvious about what we've just done? When the valve was wide open, we had a very low differential pressure across the valve, but when we throttle the valve to a fairly closed condition, the pressure drop across the valve increases substantially. We have to worry about this condition because differential pressure is our enemy. It's what causes cavitation and flashing. Let's look into this a little further. What are the actual physics that are going on? Rho VA, that's density times velocity times area. Multiply those three things together, and what do you get? You get mass flow rate. What do we call this law that would suggest that whatever I have as rho VA here at the inlet of the pipe and has to be the same rho VA here on the outside of the outlet pipe. And what about when we go through this orifice that is a representation of my control valve and we have a very narrow area where that flow has to get through? Obviously, we have to have the same mass flow rate through here. We can't, nothing's leaving the pipe. So rho VA has to be constant across here, okay? What do we call this? This would be worth a, that's called continuity. I'm sorry, that's not my test question. That's called the law of continuity, and it basically says mass flow rate is conserved down this pipeline, including through the orifice. What explains the hump in the velocity curve at what we call the vena contracta, the area of the least area of the fluid stream? Well, I already told you that about 3 slides ago. That's the Bernoulli's theorem. Remember? Well, that's because I've got to get, the velocity is high because I've got to get all the flow rate through that minimal area. But in regards to the pressure, why is that a minimum at the same point that the velocity is the maximum? That's defined by Bernoulli's. I'm sorry, I have to re-paraphrase that. The low dip in pressure can be explained by the Bernoulli's theorem, which says that the conservation of energy requires that the pressure head and the velocity head be conserved along a streamline. what happens, and there's that question. I've already given you the answer, so no $100,000 bar for you today. So what if it just happens that this dip in pressure in the middle of our control valve drops below the vapor pressure? That is a very important phenomenon to know that it's going to occur because as the pressure drops below the vapor pressure, the fluid, the liquid, whatever it was, it starts to boil. And it's boiling all through this trip through the control valve. It's boiling all through this trip through the control valve until it recovers to a pressure, P2, higher than the vapor pressure. And as soon as it crosses that vapor pressure, all of those vapor bubbles, if it were water, what we've got is a bunch of steam in here. When it recovers over the vapor pressure, all those vapor bubbles, steam bubbles, they all collapse back to water really violently with a lot of energy, with a lot of microbursts of high velocity fluid streams that you'd have to see at a microscopic level. They rip apart all the valve components. The metal gets chewed to pieces. And this could happen, I've seen it happen in a week, and I've seen it happen over the course of years. And it's fairly unpredictable, actually, as to how it will affect you. It depends on the materials of construction, how fast the fluid is flowing. A lot of different issues come into play here. But the fact of the matter is we are cavitating, and cavitation will cause damage, and it's just a matter of how long it takes before you're calling us for a new valve or new parts, or you're calling our repair service to come out and fix the valve. What if we could pick a valve that has a bigger or lower dip? You can see the blue valve there. Both valves start at the same inlet pressure. Both valves end up at the same outlet pressure, P2. Okay? It doesn't matter what the valve is that's in there. The inlet pressure and the outlet pressure are the same as determined by your hydraulic balance, which we discussed. But the point is some valves, which we call low recovery valves, don't dip down so far in pressure inside the valve as a high recovery valve, which dips way down. You can see that PV, that vapor pressure line there, obviously the valve that's the high recovery valve is going to drop below that line in this particular instance, whereas if I applied a globe valve, a low recovery valve instead, I might actually avoid this issue. So by picking the right control valve, we might actually avoid this cavitation issue. We call the globe valve it has a high F sub L, a high geometry coefficient. You remember F sub L was the term that determines the departure from the straight line ideal flow straight line to reality, which is the fact that it heals over and we end up with some maximum flow. That delta P that causes that vaporization to occur is defined by the F sub L. We square it, we multiply it by this. P1 is the absolute inlet pressure to the valve, PV is the vapor pressure, and R sub C is the critical pressure ratio. And we know all those based on the fluid. We know the F sub L based on the valve that we pick. We can therefore calculate what differential pressure across the valve will cause vaporization and therefore cavitation or flashing. And therefore we can intelligently choose the architecture of the valve to avoid this problem altogether. Why don't we do a little thought experiment? How else could we minimize this pressure dip such that it didn't drop below the vapor pressure? I've shown you the vapor pressure down here. If I had a single valve, this valve would have a tendency to start up here at my inlet pressure and drop way down, drop below the vapor pressure, and recover above the vapor pressure to P2. I would have a cavitating valve. What if I decided to put 3 valves in series and take a little pressure drop across each one? Well, first of all, it would become obvious that each successive valve would have to become bigger and bigger because we have less pressure drop available across each one to get the same amount of flow through it. But I could take this first valve and take a pressure loss and then provide some room for recovery. Then through the next valve or orifice, take another pressure drop and then take a little recovery and then take another one. If I did that enough times, I might reduce the probability that this last dip drops below the vapor pressure, and therefore I would reduce the propensity of this valve to want to cavitate. In essence, all valve manufacturers do this by creating a series of pressure drops through their control valves, in essence creating a whole bunch of orifices in one example that are all in series, and each one has a recovery zone around it. You can see that the little orifices, or the flow rate comes through the little orifices and then bigger orifices and then even bigger orifices. In essence, I've created 3 valves in series here, the goal being to get successive pressure drops, each with a recovery, such that the last pressure drop does not drop below the vapor pressure. We can do this with many different architectures. The more severe the conditions for your valve, the more expensive the valve becomes, the more elaborate the valve trim becomes. But nevertheless, we valve manufacturers have valve trims and valve styles that are appropriate to the kind of differential pressures you want to throw at us. We can even do this, believe it or not, in a plain old segmented rotary ball valve with an attenuator. We'll force the flow rate through various holes to achieve the same pressure drops in series and try to avoid cavitation. It's a little harder in a rotary valve, to be quite truthful. In some cases, we'll even take advantage of the fact that we've got some valves that have 60 pounds in the inlet, and they are headed back to a river. They're a cooling water valve. They're going to a lake, a cooling tower, whatever. There's a bunch of pipe getting it back to the river. So we have some positive pressure, P2, in the pipe right downstream of the valve. But inside the valve, the actual pressure at the vena contracta is less than the vapor pressure, and we would cavitate. And we have a vacuum in this particular point. We're below atmospheric pressure. So sometimes we take advantage of sticking a hole through the pipe and sucking air into the valve interior, and all these air bubbles provide sites for collapsing steam bubbles to give a shock absorber, more or less, and we reduce the effect of cavitation and flashing. That usually you would use that with like a very large valve, an 8, 10, 12-inch valve that's handling cooling water flow back to the river or lake. Very less expensive than a Cav 4 that's 10-inch size. Hey, there's something really different in this picture than any of the pictures I showed you. Take a second, look at that. You're going to see that the downstream pressure of the valve in this example is not above the vapor pressure, it's below the vapor pressure. Well, what the heck is going on here? What is this application called? This is called flashing, as you can see by the top of the slide. In this particular case, we come in, we're a liquid, we're above the vapor pressure, we drop below the vapor pressure, the liquid turns to vapor, it recovers to the downstream pressure, and it never turns back to a liquid because it's above the vapor pressure. This is a little different, a little easier to handle. It's not cavitating, therefore we don't need a very expensive anti-cavitation trim, but nevertheless, the fact that we come in water and we're going through the valve as a water-steam mixture, it's a very abrasive, very erosive mixture. It's like a scouring pad running through your control valve, and we need to do certain things to protect you from that. And we do that with basically the materials that we pick, the architecture of the valves, and the fact that we might use a liner in the outlet of the valve. We're going to make these all very hard materials, and a lot of times we'll use an angle valve so that this flashing fluid doesn't make a tortuous path through a linear globe valve. So by architecture and materials, we try to solve damage to flashing problems. Noise. We're concerned about that, of course. You've got environmental, equipment reliability, and safety issues going on. These are some examples of noise in the environment in which you live. There are OSHA exposure limits. You guys know all about these. You know, this dictates what kind of hearing protection your operators in the field need to wear and how long they're allowed to be in the field being exposed to that level of noise. So something has to be done about noisy valves. Even if from an environmental, safety, OSHA, good neighbor policy standpoint, like I said, you don't find that there's a need to quiet a valve. When we get to 110 dBA, we're going to tell you that we want to do something. We need to spend more of your money to save you more money downstream. So be prepared for that discussion with your valve supplier once we reach about 110 dBA. You know, noise is just an assortment, random assortment of sound pressure waves of various amplitudes and frequencies. You would think it's very difficult to calculate the noise level coming from a control valve, but it's not. We have an acoustical efficiency factor that we use to convert the differential pressure energy to two forms, heat and sound, and we can actually predict how much of that will become sound. We have an international standard that we all use to calculate the sound pressure level that's created by the control valve. We use some basic thermodynamic theory, aerodynamic noise results, some experimental results, and actually some things that we can measure about the valve physical trim characteristics, and we end up calculating the A-weighted sound pressure level in decibels, and that would be as measured 1 meter downstream of the valve and 1 meter away from the pipeline. We can reduce noise to the environment by using path treatment. We might use heavy walled pipe, or we might use insulation. This masks the noise to the immediate environment. Let us know if you've got thermal insulation, and you'll allow us to take credit for it when we do our noise sizing calculations. Make sure if you're out for bids, you tell all the valve suppliers that they all have the same luxury, or they have not the luxury at all. We're going to use source treatment to reduce the noise level if it's by creating something different in the valve to not let the valve even start to make noise. And we can do this by the proper selection of the trim, by using a diffuser, a silencer. We've got different ways to do that. You can see here that thermal insulation, for example, is worth 10 dBA of noise attenuation if you give us 3 inches thick of insulation, calcium silicate, for example. Anytime we have to put an elaborate trim in a valve to reduce noise, it essentially is going to have the same characteristic. It's going to break the flow stream up into a whole bunch of independent flow streams that we hope don't interact. When you get these flow streams interacting, these jets, we end up with supersonic shock cells, and we get a lot of noise. So this has to be carefully done, and the spacing of the holes and the size of the holes are engineered based on the differential pressure across the valve. And these noise attenuating trims take different forms and different levels of cost, but the point is they all essentially break up the flow stream into a whole bunch of flow streams. We'll use a silencer in combination with a diffuser in order to reduce noise if we can't do it by the valve trim alone. The diffuser is this device. It's just nothing more than a piece of pipe with a whole bunch of holes, and we'll use up part of this system pressure drop as drop across the diffuser, which reduces the pressure drop across the valve. And by reducing the pressure drop across each one of those devices, we can frequently end up with a total combined noise level that's less than we could do with a valve alone. If we still need to do some attenuation, we'll do that with some noise absorbing material in the silencer. It'd be a Teflon base packing material or whatever, in order to be corrosion resistant and yet absorb noise, like a muffler, if you will. So let's talk about a few things you wish you thought about before you get to meet the plant manager. I see we're running a little short of time here, so I hope you can stick with me for just a few minutes more. Welded valve installation issues. Hey, if you're going to weld the valve into the pipe, you should know things about the pipe material. Your pipe design spec has valve allowable materials. What's the schedule? How are you going to put it in the pipe? What P number is used for welding? Does that P number require post-weld heat treatment? That's a process in which you're going to lay some ceramic blankets under high voltage around the welds that are connected to our valve, and you're going to heat those welds to about 1400 degrees to relieve the stresses in the weld. And we've got some valves that will hold up fairly well at 1400 degrees. Most of them do not. So we need to come up with ways to keep you from hurting our valves after you install it, and then you're going to post-weld heat treat it. Know that when you weld chromoly materials into your piping system, that's going to be a P5 weld. You're probably going to have to do post-weld heat treatment unless you control the carbon content, and you need to refer to ANSI B31.1 to know when you can do that, when you can take exception to post-weld heat treatment. If you can't, we'll frequently add 6-inch nipples, which in the power industry they call those safe ends, to the ends of our valves, or we might put reducers on the valve if your pipe is a different size than our valve. Either one of those will move the final field weld and therefore the final post-weld heat treatment well away from the valve body, and we can eliminate the need to take the valve apart to take those sensitive components out when you do your post-weld heat treatment. And always order chemical and mechanical test reports with your valve if your valve is to be welded into the line. You're going to need that to support your determination of the weld rod, the weld process. Your certified welders need to see the CMTRs before they should feel confident that they're using the right weld materials to put the valve in line. If all else fails, consult your valve supplier for recommendations regarding valve disassembly. prior to post-weld heat treatment. You know, if we tell you that the trim's got to be taken out before you do that, well, let's make sure that we order an extra gasket set. So when you take it apart, we've got new gaskets to put it back together. Do not, if we made a mistake and it did not pay attention to the fact that your valve was mounted up against a wall, and you've got a positioner, let's say, mounted on the valve actuator, it's now up against the wall. And your instrument mechanics are going to read you the riot act because they can't get behind there, they can't get the cover off, they can't do a valve calibration. So, hey, make sure that you tell your valve supplier what side of the valve, in relation to which direction the valve is flowing, what side of the valve would you like the positioner on. Even if we hose this up, if we do hose it up or you hose it up, well, you're going to be compelled to want to spring the actuator. I'm sorry, rotate the actuator, spin it around so that the positioner ends up on the side that you want it. Do not do that with the plug on the seat. You're just going to score the plug, and we're going to get a bad shut off. So if you got to do that, make sure that if it's a fail open valve, you're okay. The plug is off the seat. If it's a fail closed valve, you got to put air in the actuator to raise the plug off the seat. Then you can spin the actuator. Then you can take the air off, and you're okay. All right. Boy, if you're going to blow down a piping system, it's new construction, and you got to blow down a piping system, get rid of weld slag and dirt and lunch boxes that are in the pipe. Put some sacrificial startup trims in there. You know, we'll ship you a valve with startup trim in it. We'll keep the real trim at our service center. When you're done with your blowdown of your piping systems or your flushing, we'll come back and install the right trims, and we'll throw away the flushing trims. And whatever you do, after you install a severe service control valve, please ask the valve manufacturer's service team to come out and run a calibration check and make sure the valve is completely operational before you start it up, because you've spent a lot of money for that valve. Let's make sure that it's ready to run. Do the engineering that's required to know what the valve P1 and P2 are, okay? I won't bother to get into this story about sky vents because we're running short on time, but make sure that you know whether or not this valve will be used somehow for a hydro test. Know also, will it be used, are you going to chemical clean the piping system with the valve in line? What chemicals are going to be used? How do you think they're going to affect the control valve? Okay. Will the valve ever be expected to shut off in the reverse flow direction? I was at a power plant in Wisconsin not too long ago, and the customer said, Mike, you know, I forgot the process. There's a process. I think it involved hydro testing. He said, we actually are going to need this valve to shut off in the reverse flow direction. Believe it or not, most control valves by nature do not do that very well. They can shut off pretty well in one direction, but unless we arrange for it, they don't shut off well in the other direction, and we end up collapsing elastomeric parts. We can damage them. So if it's going to have to flow in the reverse direction sometime, tell us. If you're going to put in a very expensive valve in the line, it would be a good idea to install an upstream and a downstream pressure gauge so that we could use those pressure readings, the P1 and the P2, for troubleshooting at a later date. Use Teflon packing whenever you can. It's the lowest friction available. Friction is a control valve's enemy. You get the best control valve, and what I mean by that is you get the best production cost, the highest profits, the lowest variability if you use a low friction valve. So use Teflon packing whenever possible. And listen, if this is a high temperature process, a very high differential pressure, and you want this control valve to shut off tight, we would prefer, all of us valve manufacturers would prefer that you use a different valve for that. Use a valve expressly built for the purpose of isolating high temperature, high pressure drop services. Motor operated gate valve, a manual gate valve. Your very expensive severe service valve is going to last a lot longer if you do. Hey, first of all, let your maintenance of your severe service valves to your valve supplier service company. I can't stress that enough. They're really trained to take care of them appropriately. If you can't, know where to find the valve serial number and have it before you call your valve vendor, because they're going to need that to give you recommendations about how to take care of this, what parts go into it, and so forth. There's an adjustment in most control valves called the spring precompression. We call it the bench set. You need to know the significance of that and know how to set it. Customers frequently set that incorrectly. We end up with valves that start leaking through immediately and have significant trim damage. The simple process of connecting the actuator stem to the valve stem is often done improperly. read the instruction manuals. Make sure you know how to do that. It's the only way to ensure that you get the appropriate shut-off thrust of the plug against the seat. Know how to calibrate the valve positioner. A poorly calibrated positioner will quickly turn your most expensive severe service control valves into useless you-know-whats. Anytime packing is replaced, make sure you inspect the condition of the stem and the packing bore. It does no good to replace packing in a valve if either one of those are in bad shape, because it's just going to start leaking right away again, and you've wasted your time opening up the valve and replacing the packing. And please, I said this really long because this is one of my pet peeves, and I go past my critical valves and plants that I've sold valves to, and I look at the pressure gauges that show the supply pressure to the positioner. If you don't have the right air pressure as defined in the nameplate delivered to the positioner that's on the valve, you're going to end up with a valve that's either A, not going to stroke all the way, or B, it's going to leak through in short order, and you're going to be very disappointed with the lifetime of your severe service valve. So please make sure the air supply is appropriate. I think that's all I had to say for today. Thank you very much for your attention, and now I'll turn it back over to Robert to field some questions.
Well, thank you, Mike. We got through a lot today. You can see on your screen Mike's contact information. If you want to get in touch with Mike or your Novaspect account manager for further information, please do so. Mike's available now to answer any questions. So please raise your hand using your control panel, or you can type a question into your control panel as well. And again, if you don't want to share your questions today, please feel free to contact Mike directly or your Novaspect account manager. Okay, it's a quiet group out there today. Remember, this session was recorded. It will be available on Novaspect.com